Hello. In this video about derivatives, we are going to review the continuity of a function. The prerequisites are to have some knowledge of what a function's limit is and basic mathematical notation. We don't need to know much about limits, don't worry. We say that a real function f is continuous at a real point called a if the limit when x approaches a of that function is equal to f of a. How do you calculate all of this? We're going to do it not just in one step, but in three. For a function to be continuous, three conditions must be satisfied. First, the function must be defined at the point where we are asked to determine if it is continuous or not. In this case, it is the point a. Therefore, I have summarized it in this way as f of a must be defined. It could have been said that the function exists in that point a. Second step. We have ensured the existence of this part of the equality. Let's move on to the second one. The limit as x approaches a of the function f of x must exist. If that limit doesn't exist, the function is not continuous. The third requirement is simply what we put up here, and that is that the two values we have calculated in steps 1 and 2 match. It means that the limit and the function at point a match. Let's see an example. We're going to study the continuity of the function 1 over x at the point x equals 0. At the beginning, right after reading this function, you should think something unusual is going to happen here, something strange is happening. Why? Very easy. Because the function 1 divided by x is not defined in x equals 0. We have 1 divided by 0, and it cannot be divided by 0. So the first condition of continuity is not fulfilled. Remember that the first one is that the function at the point we are being asked about exists or can be calculated. In this case, in point 0, the function cannot be calculated, and therefore the function is not continuous. Anyway, we could see that the limit of the function when x tends to 0 does not exist. In the graphical representation, as I approach 0 from the right, the function tends to positive infinity, and as I approach from the left, it tends to negative infinity. Therefore, this function is not continuous in point x equal to 0. Watch out, the function is continuous at any other point, but in the point 0, it is not continuous. Let's take a look at one of those examples you all like so much, which are piecewise defined functions. We have a function that is defined in 3 pieces. In reality, the domain of the function goes from 0 to 8, as you can see. The smallest value is 0 and the largest value is 8. From 0 to 3, the function is equal to minus x plus 15. It has this expression. Between 3 and 6, the function is x squared minus 8x plus 26. And between 6 and 8, the function is 2x plus 2. X represents the time in hours elapsed since the beginning of the session. We are talking about how the value of a certain action during a session is given by this function. Therefore, x represents the time in hours elapsed since the beginning of the session. We are asked to study the continuity of the function f of x. In this case, before we begin, I have represented the function using the well-known software program called Mathematica. The graphic does something like this. As you can see, I have 3 pieces. From 0 to 3, there is a function. From 3 to 6, there is another function. And from 6 to 8, there is another function. I think it is quite clear that here is a kind of jump. Although the program has drawn a vertical line here, connecting these 2 points, in reality, there is some sort of jump. In this case, it seems like the function is not going to be continuous. But we need to analyze it analytically to confirm. We will see how it is done. Let's start with the point that it is equal to 3. Why? Notice that this here is a polynomial of grade 1. This is a polynomial of grade 2, and this is a polynomial of grade 1. The 3 are polynomials. These 3 functions are always continuous in the domain that is required at this time. The only problem that can arise in this function is the following. In the points where I switch from one function to the other, for example, in 3, I go from working with the first function to working with the next one. Therefore, in this point, in 3, there may be some problem. There may also be some problem in the point 6 when I go from this function to 2x plus 2. In the rest, I insist, any polynomial is continuous. Therefore, I would not need to study the continuity in any other point. Let's start with the point 3. What happens in this point? We will have to start with the 3 steps that we have mentioned before. First, does the value of the function at point 3 exist? Yes, of course, we need to go back a moment. What expression do I use to calculate the value of the function in 3? Where is the 3 included? Here. The x is less or equal to 3. The equality is included in this step, therefore we will use this expression, that is, we will replace the x by 3 in this function. How is this calculated? Look here, minus 3 plus 15 equals 12. The second step, does the function limit exist when x tends to 3? The answer is, I do not know. How are we going to calculate this limit? We'll have to do it from the right and from the left to check if it exists. If both limits, from the right and from the left, exist, then the limit exists. And if they don't match, the limit doesn't exist. It may exist from the right and from the left, but the limit in general may not exist. It is very easy to calculate. We are going to start calculating the limit when x tends to 3 from the left side of the function. But what does it mean from the left? From the left, allow me to go a little back again. If this is the value 3 from the left, we are taking the function minus x plus 15. And from the right, we will take the other, x squared minus 8x plus 26. So, we calculate the limit when x tends to 3 from the left. I substitute the function f of x for the corresponding expression, which is defined before the 3, which is minus x plus 15. How do we calculate the limit? What we do is replace the value of 3 in this expression. And I get minus 3 plus 15, which is equal to 12. Good, we have one limit. Calculate it as I approach 3 from the left. How much is the limit when I approach 3 from the right of the function? We do exactly the same thing, but now we substitute the function for the corresponding expression. That makes sense to the right of 3. In this case, it is x squared minus 8x plus 26. We substitute 3 in each of the values of x and get 3 squared minus 8 by 3 plus 26. The answer is 11. So, this limit does not exist because on one side it gives us 12 and on the other side it provides 11. They are different values, the limit does not exist. So, what can we deduce? That the function is not continuous in x equal to 3. That was evident from the graph. It seemed that there was a jump. As you can see here we see a jump. That jump could not be here if the function has to be continuous. We saw 3. Let's go now for 6. What happens in point 6? We have to do the same. First step, how much is the function in 6? It is very likely that we already remember where the 6 was included, in which part of the expression. I'm sorry, I'm going back a bit again. Let's take a look here. The x between 3 and 6 included is the corresponding to this expression. So we are going to take this expression to calculate how much is the function in 6. The function in 6 is equal to 6 squared minus 8 times 6 plus 26, which gives 14. Next step. Is there a limit of the function when x tends to 6? The same as before, we have to analyze from the left and from the right. Now imagine that I am getting closer to x from the left. Then what expression does make sense when I get close from the left? X squared minus 8x plus 26. How is the limit calculated? Replacing x with 6. And I end up with the same expression as before, which is equal to 14. Let's now calculate the limit, but from the right of the function. What expression does make sense from the right of 6? It is 2x plus 2. How do you calculate the limit as x approaches 6 of 2x plus 2? By substituting x with 6. Therefore, it would be 2 by 6, which is 12, plus 2, which is 14. 14 and 14, both limits from the right and from the left coincide. We can advance to a next step. The third step is simply to compare that the limit value and the function value in that point coincide. In this case, we have 14, 14, 14, and the function is continuous when x tends to 6, and the height value is 14. What have we seen in this session? We have reviewed the concept of continuity, and we have seen some examples of continuity. I hope this lesson helps us. Thank you very much for your attention.